Welcome, everybody, and thanks for joining us. Today, we have Professor Juan Maldacena from the Institute for Advanced Study, who will tell us about gravity and black holes from an interacting quantum system. And this is, I think, a talk based on his latest paper. Juan, it's a delight to have you speaking with us.
Okay, it's a pleasure to be there, and yeah, since we are a relatively small audience, let's please interrupt me for questions, and so we can have more of a dialogue, perhaps. So I was telling Jeff that I had two versions of this talk. This is a bit more general, and then so we'll start with this one. It's a shorter than an hour. Then we can go onto some of the points later, perhaps. Very good. So let's start. The main point of the talk, well, the main point of this talk was to talk about the relationship between gravity and black holes. Now, there is an important hypothesis in the study of quantum aspects of black holes, which is the idea that black holes can be viewed as quantum systems. Sometimes we call this central dogma, central hypothesis. And this hypothesis really goes back to, in some sense, the work of Bekenstein and Hawking and the interpretation of that entropy. And it's in some form in later developments also. So the idea is that the black hole is, if you look at the black hole from the outside, it can be described as a quantum system with s degrees of freedom. So where s is the area of the black hole in Planck units. So by degrees of freedom, we just mean qubits. So number of qubits is this. And here I'm not making a difference between qubit, Majorana fermions, or whatever. So it's just a statement about the dimension of the Hilbert space. And the idea also is that it evolves according to unitary evolution, as seen from the outside. So the idea is that if you do any measurement from the outside of the black hole with arbitrary high precision, then you will see that the black hole is indistinguishable from some quantum system. The hypothesis itself doesn't tell you what the quantum system is or what the Hamiltonian is. But so this is a hypothesis, and it's a non-trivial hypothesis about gravity. And in fact, Hawking argued that this hypothesis is not true, so that information is preserved. So if this hypothesis were true, then information would be preserved, while Hawking argued that it was not preserved. And now, in some very, very special cases, we have some candidate quantum systems. So we can have specific quantum systems that are supposed to describe specific black holes, so in specific gravity theories. So what we'll do here is we'll review one special case. We'll describe one special case of this relationship. And this is the case where the quantum system is simplest. And by simplest, I mean that it involves ordinary quantum mechanics as opposed to quantum field theory. So it's really a system involving a finite number of qubits. And the black hole is a little more involved than in other examples. So the black hole is a little more complicated. I will describe it. And this system has the special property that the black hole involves sort of standard Einstein gravity. So there are somehow simpler quantum systems where the black hole, well, the analog of the black hole is in a more exotic theory of gravity. But so this is the simplest example that involves an Einstein theory of gravity. So the quantum system we are going to talk about, so will be built out of some elements. So roughly speaking, is the simplest elements you could imagine, sort of harmonic oscillators and qubits, two-level systems. Now, two-level systems, you can view it as a fermionic oscillator or a pair of Majorana fermions. And actually, to write the Lagrangian, it's better to think in terms of these fermions rather than to view these two-level systems as qubits. Now, we will need a large number of these elements because black holes have a large entropy. And we'll also need some interactions because black holes thermalize quickly and are maximally chaotic. So there is a sense, a very precise sense in which black holes are chaotic, and that chaos is related to the properties of scattering of particles near the black hole horizon, and you can do a relatively simple calculation that shows that whatever system describes the black hole should be a chaotic system. So the type of Lagrangian we are going to imagine will have some free terms. So these were like harmonic oscillators and Majorana fermions, that a bunch of two-level systems. And then we'll have some cubic terms and also some quartic terms with the various coefficients. That's the generic structure of the Lagrangian. Now, we don't know what the general Lagrangian like this does, because it's hard to solve, especially when these interaction terms are important. But we have a gravity dual for one special case, which in some sense was found by luck. So there is a special case for which we think we know the gravity dual. And here by the word luck, I mean it was found using string theory. And I will not explain how it was found, but we could discuss that when we go to the discussion session. So so let's talk a little more about the details. So first we'll take the harmonic oscillators to 0 to simplify the gravity solution, or equivalently we'll consider a higher energy limit where these frequencies are small. We also have the gravity solution where they are non-zero. We can also discuss that. So the symmetries of the theory we are going to consider are going to be the following. So first, we'll have an SUN symmetry with n very large, and then we'll have an SO9 symmetry. And then in addition, we'll have some supersymmetries. So the supersymmetries will be present if we restrict the model to the SUN singlet sector. So when we do quantum mechanics, well, in some descriptions, people say this SUN symmetry should be gauged. Now, when we are in quantum field theory and we gauge a symmetry, we are introducing a gauge field which contains some dynamical modes and so on. When we talk about gauging in quantum mechanics, all that we are doing is we're adding some gauge field A0, and we are imposing that the only role of that component of the gauge field, which is non-dynamical, is to impose a constraint, which is to just impose that you look at the singlet sector. So there is the gauge version of the model that where you treat the SUN as gauge symmetries, and that amounts to looking at the singlet SUN singlet sector, and that has some additional supersymmetries. So in general, we don't have supersymmetry only when we look at the SUN singlet sector. Okay, so but in addition, we think that the strong coupling, the singlet sector is the one that has lowest energy. So even if you didn't gauge the symmetry, then dynamically you would be you would go to this singlet sector anyway. Okay, so we have the symmetries, and then we have some variables which transform in different ways under the symmetry. So all the fields of the model, or the let's say harmonic oscillators or particles we have, are going to be in the adjoint representation of SUN. And we can write them as n by n matrices with sort of, you can view this as a fundamental anti-fundamental index, and we say they have 0 trace, so then they are in the adjoint. Then we also have this SO9 symmetry, and the bosonic fields transform in the vector representation or 9-dimensional representation of SO9, more or less like a coordinate in R9. And then we also have fermions which transform in the spinor representation of this SO9 group. Very good. So now we can write down the explicit Lagrangian we are talking about. So there is a free kinetic term for the scalar fields, for the scalar variables. And then we have similar thing for the fermions. And then we have some interaction. So we have this quartic term. So this is like a quartic potential for the bosonic variables. And then we have a cubic term that involves a type of Yukawa type interaction between the fermions and the scalar fields. But I emphasize these are just two-level systems, and you can view this as a kind of anharmonic oscillator where you have a quartic potential as opposed to a quadratic potential. I mean, this potential has some directions along which it vanishes. So this is the direction where these matrices commute, but that's a relatively small number of dimensions compared to the total number of dimensions, which goes like n squared. So yeah, maybe I didn't say that, but maybe I'll emphasize that the number of dimensions that we have is n squared. Well, n squared times 9 is the number of bosonic directions. Now this Lagrangian can, so here it was written in terms of matrices, and we have it in matrix form. We could also write it more explicitly by writing out all the components of the matrix, and A here is an index that runs in the adjoint representation. It goes from 1 to n squared minus 1, which is the dimension of the adjoint representation. So we have all n squared times, well, roughly n squared. I said before n squared is n squared minus 1 times 9 variables. We have the fermion fields, and then this potential involves so the commutator of the matrices becomes just something that contains the FABC, or the structure constants of the group, the SUN group. So these are the ones that appear in the commutation relation of the generators or the Lie algebra. And then similarly, we have a term for the fermions. So this gamma I alpha beta is a 9-dimensional gamma matrix, and it's just the invariant tensor that converts connects the SO9 representations to the 16-dimensional spinor representations, so that this interaction is SO9 invariant. Now, like any quartic theory in quantum mechanics, this parameter that appears here has dimensions of energy cubed. Okay, this is not something due to this exotic Lagrangian. This is even if you had a simplest quartic potential in quantum mechanics, you also would find that the coupling constant that appears here would have dimensions of energy cubed. And this is the only this is a dimensionful coupling of this theory. And we put this factor of n in such a way that when we consider quantum corrections to this Lagrangian, the interactions are proportional to lambda. Okay. So without any additional powers of n. So the power of n is put here to cancel other powers of n that come from the fact that we have many fields. So these interactions, roughly speaking, each interaction here involves n other fields. And so these n fields run into the loop, and they give factors of n in the interaction. And the rules for counting these factors of n are well developed, and I'm not explaining them, but they are called Atoft counting. Anyway, so the point is that there is this coupling constant that is dimensionful, and if we consider energy is bigger than lambda, the theory will be free, will be very weakly coupled. But for energy smaller than lambda, or lambda to the 1/3, the coupling will be strong. Okay. So in most of this discussion, so for the rest of the talk, we'll discuss this model at finite temperature. So here there is another diagram of the relevant energy scales for our discussion. So if we consider energies that are high compared to lambda to the 1/3, the theory will be essentially weakly coupled. And for energies smaller than t, and here when I mean energy, I mean energy per particle, or maybe some quantity like temperature. So in other words, we could read this diagram as saying that when the temperature is bigger than lambda to the 1/3, we can analyze the model simply using weakly coupled, essentially almost classical physics. And then when the temperature becomes lower than this scale, lambda to the 1/3, we will have strong coupling, and it will be hard to analyze the models in a very direct way. So we will discuss some techniques to analyze the model. So one will be the gravity discussion, and then there will be some numerical work that was done by some people. I will review that later. Now here we're considering making the temperature smaller than lambda and taking very large n. And then the model has some other features when the temperatures or the energies become very, very tiny. And I will not discuss that. So new features appear at very, very tiny energies, very tiny temperatures. And we will not discuss those. So those are temperatures which scale like some inverse power of n. So we're going to assume that the temperature, let's say, is smaller than lambda to 1/3, but stays fixed as n goes to infinity. Now, just some of you might be familiar with the SYK model, which is a simpler model that contains purely Majorana fermions and some interactions among those fermions. In that model, there is also some coupling constant J, which has dimensions of energy, and the model is simple at temperatures or energies bigger than J, and becomes strongly coupled when the temperature becomes smaller than J. So the analog to J here is this lambda to the 1/3 that divides the weak and strong coupling regimes. And also in SYK, there is some region of very tiny energies and so on, where the behavior changes a little bit compared to the region where you take just n to infinity and keep the temperature finite without scaling the temperature with n. Okay, so are there any questions? Am I going too slowly?
No, I think this is great. Actually, I have a question.
Yeah.
So then, are you taking the temperature as proxy for energy? So when you scale,
Yes.
you scale n with fixed temperature, that's the same as
Yes.
scaling n with fixed energy. Is that right?
Yes. Yeah. Maybe instead of talking about energy, I should have simply said about temperature. Talked about temperature. So when the temperature is bigger than this scale, then the model is simple. When the temperature is lower than this scale, then the model is more complicated. Let's just think in terms of the temperature. So we are
okay, correct. Thanks.
How the temperature. Yeah. I probably didn't say the simplest way. So here I'm going to make some historical comments about this model. So this model was originally found as an example of SUSY quantum mechanics in that paper. Then it was used to discretize membranes in 11 dimensions. And perhaps the most interesting application of the model was one that Banks, Fischler, Schenker, and Susskind did in 1996, where they said that this model describes the 11-dimensional S matrix. Now, in the BFSS application, they were considering a very tiny energy, so energy that was very small and goes to 0 when n goes to infinity. So actually energies that go like 1/n. So that's the regime where the model is related to the 11-dimensional S matrix of M theory. Now that's not the regime we're interested in here. In fact, the perspective that we're having in this talk was in this paper we wrote in '98, and that relates the model in this slightly higher energy regime to black holes. So I'll discuss that now. So the idea is that this quantum mechanics theory is related to a 10-dimensional black hole in a very specific gravity theory. Now, let me just make some preliminary comments about black holes. So black holes exist in general theories of gravity in many dimensions, 2, 3, 4, 10, whatever. So they are very generic objects. They have a horizon, they have entropy, they display Hawking radiation, etc. So they don't depend particularly on the number of dimensions. Now, there are various types of black holes. So you can have an uncharged black hole. This is just a solution of Einstein's equations with, let's say, zero cosmological constant. That's the first black hole that was found, the so-called Schwarzschild black hole. Now, you can also have charged black holes. So these are solutions of Einstein-Maxwell theory. So you have the Einstein action that describes gravity, and then you have a U1 gauge field describing something like electromagnetism. And then you can have a black hole that carries charge. So there's some non-trivial flux on the sphere surrounding the black hole. And then you could also have a slightly more complicated theory where you have both curvature both the Einstein term and a scalar field, and also coupling between the scalar field and the U1 gauge field. And if you didn't have this coupling, I mean, you might say, why are we putting this coupling? Well, that's first of all, that's the coupling we'll have in the theory we would care about. But also, if we didn't have this coupling, then the charged black hole would be essentially the same as in this theory, and the phi field would be constant. However, if you have a coupling like this, if you have a charge configuration, then you notice that this coupling implies that the energy contained in the flux will depend on the value of phi. So so then the value of the scalar field phi will want to vary as in configurations that have non-trivial electric charge or magnetic charge. Okay. Now, the black hole we will be interested in is a black hole with a scalar field that will be a solution of an action of this type. Okay, so we'll have gravity plus the scalar field and the U1 gauge field. And in fact, the idea is that this model describes not this complete black hole, but only the black hole in some special limit, or in other words, a particular part of its geometry. So let me just explain how that works. So if we look at this black hole and we plot roughly what the geometry of the black hole is. So we have flat space, 10-dimensional flat space far away. This whole thing is SO9 invariant, so there is a kind of 9 sphere here. And then when we go to low temperatures, we find that, well, there will be some horizon, the horizon of the black hole, but there is a region of the geometry near the horizon that roughly has this shape. By this shape, what I mean is that as you come from the outside, the sphere shrinks and then expands a little bit when you go closer to the horizon. Now here, because we have, and the scalar field also changes. So here I'm drawing the sphere in submetric, which is relevant to how strings, how strings will see the metric. So we get a different picture in Einstein frame. This is just a comment. But if you go to lower temperatures, then what you find is that this region becomes longer and this neck becomes narrower. And then if you take, you can take a limit where this neck becomes very, very narrow. And then you get the kind of decoupled geometry, which looks like the near horizon geometry of such black holes. But because we are going to low temperatures, there could be a big distance between the horizon and this region where the neck was becoming very small. Now, because this neck is becoming very small, the curvatures in so-called string frame are becoming very high, and we cannot really trust the gravity solution in this region of the geometry. But we can trust the gravity solution once the sphere. So this diagram is basically representing the size of the sphere. And so when we go very close to this neck region, the size of the sphere is very small and we cannot trust it. And when we get further, the size becomes larger and we could trust it. So if we are low enough temperatures, the horizon will be far from this region and we will be able to trust this geometry. So because of all these words that I'm saying right now, that's the reason that this example is a little more complicated. That's related to this varying scalar field that we have. Okay, now this region here is a region where also the G00 component of the metric becomes larger, and the G00 component of the metric becomes very small as you approach the horizon, actually becomes 0 at the horizon. Now, why am I talking about the G00 component of the metric? Well, that's essentially the relativistic version of the gravitational potential. So any particle that is in this geometry will be pushed to the horizon, any massive particle. Now, in a suitable, let's say, frame, the action, so the metric, so when we have a metric and we have a scalar field that is varying, so we can define different so-called frames. By frame, we mean that we can multiply the metric by various powers of the scalar field, or various exponentials of the scalar field. And if we multiply by a suitable factor, then the metric is ADS2 times S8. So in this so-called frame, the size of the S8 is constant. In the string frame is the particular power that appears here. The sphere will shrink to 0 at the boundary. Now here, this is the metric of ADS2, that's a space with this metric. This is the time direction. And what we were calling the boundary or the top of the previous picture is set equal to 0, where the GTT component of the metric becomes very large. And here I'm writing this metric at 0 temperature so that the horizon is infinitely far at c equal to infinity. Now, in that particular frame, the action just has this overall factor. And anyway, so now one.
Can I just ask a question that may be related or not? I'm not sure.
Yeah,
but
yeah,
where does that factor of 15/4 come from?
Oh, sorry, it's actually 25/4, but it comes from solving the equations. I actually realized there's a typo now.
I remember the 25/4. I'm just...
Yeah, sorry, I had the wrong factor.
Okay,
so,
thanks.
Yeah, let me see. It basically comes from, so when you solve, so when you write it in this way, the numbers that appear here depend on the number of dimensions you have. So where you have 8 dimensions versus 2 dimensions here, and that gives rise to this factor. So if you had so let's ignore the fact that we have this overall factor. If you have the Einstein equations, if you have something like this, a charged black hole in some number of dimensions, the factor that appears here depends on the number of dimensions you're in. Is that okay?
Yeah, that's good.
Sorry. Yeah, well, I kept making that mistake. But anyway, so this factor is actually correct, and it's important for what I'm going to talk about now. So this part of the metric contains has a scaling symmetry, so we can rescale time, the time direction and the set direction by some constant, and this will be invariant. So the factors of kappa from the numerator and denominator cancel, but this sigma factor, the scalar field will not change. Will change under the scaling, and because it's appearing in the action in this way, it will shift the action by some constant delta, and delta will be 9/5. And so the full action is not invariant under the scaling, but the action changes by an overall factor. What that means is that the equations of motion will actually be invariant. So all of, let's say, classical physics around this background will be scaling invariant. And this factor is sometimes called, so people have found things similar to this in condensed matter, and they call this hyperscaling violation exponent. I think Landau Lipschitz discusses called the symmetry a scaling similarity. So symmetry, well, not a symmetry, similarity or a transformation which rescales the action. And it's common when you have some simple systems. Now, this scaling is as good as a symmetry in constraining the results of classical computation. So we can, it imposes various constraints. And I should emphasize that this similarity is, or symmetry of the classical equations, is not an obvious symmetry of the matrix model. So it's not something you could easily see from the matrix model side. In fact, it's not a true symmetry of the classical matrix model, for example. It's something that emerges once you consider the strong Kaplan limit. And if we make the SYK analogy, it's somewhat analogous to the almost conformal symmetry that the SYK model develops at low temperatures. Now, for example, this similarity, the scaling similarity constrains the free energy of the black hole. So tells us that the free energy should scale like the power of the temperature to this exponent delta. This is because when we apply the symmetry, we are rescaling the size of, let's say, the Euclidean time direction, for example. That's the same as rescaling the temperature. And so the scaling with the temperature should be determined by that exponent we found before. I should have emphasized that this exponent comes from just the particular action that we have in gravity. So this this action is part of the 10-dimensional supergravity action, so sometimes called the type 2A supergravity action. So it's a very definite action that I haven't written, but it contains various fields, but it contains in particular a two-form field and a scalar. So the action takes this form after you dualize the 2 form to an 8 form. And you get this, and you define a scalar field, and well, you work out the numbers and you get this 9/5. So it depends on the details of that action. Now, just as a comparison, if you had scale invariant for a system like in SYK, it would mean that the partition function should be invariant under scaling. So the action should just be some constant. And that's the so-called extremal entropy for those cases. In this case, it's not a constant as a function of the temperature. And we can determine some other factors like the lambda dependence by just dimensional analysis. The whole thing should be dimensionless. And then we can also determine the factor of n squared by some large n counting. So those Toft counting arguments we were talking about, that can be determined from the matrix model side, but also from the gravity solution. You can also easily determine this overall factor of n. Now, this behavior was a prediction that was checked by a numerical Monte Carlo calculation of the thermal energy of this quantum mechanics model. So what these authors have done, so this is the latest paper that they had. They've been doing this over many years with various combinations of authors. And the idea here is the following. So you take this model, you take the matrix model or the quantum mechanics theory, and you put it in Euclidean time on a circle, whose length is the inverse temperature, and then you calculate the partition function by using a Monte Carlo numerical. So you do the path integral using Monte Carlo techniques, and you get some answers. And the answers are these dots that you see over here, and the gravity prediction is this black curve. Okay. Now notice that the diagram here contains the temperature divided by lambda to the 1/3, right? So that's that parameter that we thought what we said would be relevant. So when the temperature over lambda to the 1/3 is very large, that's when the free answer is simple. So that's this region far away here in the diagram. That's determined, as we said, by classical physics. When t over lambda to the 1/3 is very small, that's the region that is supposed to be given by supergravity, right? And indeed, we see that these points here start lying very, very close to the supergravity answer, fairly close. I mean, the error bar is about 13% for this point. This curve is not just the power law, but the overall coefficient is also known. So I didn't write down here the coefficient, but this is something you can calculate using gravity, it's a specific coefficient. And then, so this is a precise prediction that you can go and check, and they indeed checked it, and they got a fairly close agreement. So this is an interesting case where the entropy of a black hole is being computed by a numerical calculation. So in other examples where black hole entropy has been matched to a gravity answer, it's been done through other techniques. So for example, for extremal black holes, which was the first case where this was done by Strominger and Baffa, it was done for supersymmetric black holes and using some techniques special to supersymmetry. Another general way in which it was done, it's when the black hole has some region where it's close to ADS3, And in that case, we can use the symmetries of ADS3 and the symmetries of the corresponding CFT, something called the, and that allows us to use something called the Cardy formula to compute the entropy. So in those two cases, we use very heavily the symmetries of the theory. Here, we are at non-zero temperature. And these authors have done just a direct numerical calculation. So it looks like a fairly first principles computation of the entropy in the matrix model. Now, I should say that when they do these computations, they take some small value, some value of n, which is maybe 16 or 24, and some number of lattice points in the time direction, which is roughly of this order of magnitude. And then they do this for various values of n and various values of lattice points, and they extrapolate to the continuum limit. And these points here are the result of those extrapolations. I think one side comment is that maybe I'll say, yeah. Notice one point is that the scaling symmetry or similarity that we were talking about is present at very low temperatures, but is violated at higher temperatures. It's not present at higher temperatures. And indeed, this curve is different than the black curve, which is the one implied by that symmetry. Okay, now one interesting point about this numerical calculation is also that these deviations from the classical gravity answer are governed by the alpha prime corrections of some higher curvature corrections of the action. And this computation allows them to predict the values of those alpha prime corrections, something that has not been analytically computed yet. So in some sense, we can say that this numerical calculation is actually more advanced than the analytic understanding of this type of black holes. Now, one fun thing one can do is one can notice that here they got fairly close agreement for these values of n and lattice points, and one can try to translate that to estimate the number of qubits that you would need to actually simulate this on a quantum computer. So imagine that you wanted to simulate this quantum system on a quantum computer. How large, how many qubits would you need? Well, you can estimate the number of qubits as follows. So n will be the number of qubits. There will be a factor of n squared because for all fields we have n by n matrices, so we have a factor of n squared. That will be this factor of 16. Then from the 16 Majorana fermions, you can group them in groups of 2 and make qubits, so that's 8 qubits. And then we have 9 scalar fields, and scalar field is a bit like a harmonic oscillator, which contains many levels, but you don't need to consider the infinite number of levels. You can just truncate that Hilbert space, and you should truncate it to a number of levels, which should go from the scale lambda to 1/3, which was this UV scale where the model becomes strongly coupled, to some, let's say, infrared scale, which is where you can put a little tiny harmonic oscillator frequency or mass. And yeah, so this is some small number, and well, you get some number which roughly 7,000. I mean, this number has some error. It's just an order of magnitude. Now, people say that the number of times it takes to double the number of qubits in the quantum computers that have been built is about 5 years. So if you go from 50, which is the number we have now, to 7,000, that apparently you need 30 years to get to 7,000. So we can perhaps say that in maybe 30 years, we will be able to simulate these models on a quantum computer, and we'll be able to probe these black holes. Now, this of course is very optimistic, and we are not including quantum error correction, which could multiply these numbers by a big factor, like maybe 1,000. So maybe it's not as optimistic as one would like. But well, this number is of course much bigger than the numbers quantum computers have today. So it's not possible to do this with the current day computers or quantum simulators. Okay, so now we will look at another interesting property of the black hole, and these are the quasi-normal modes, and these are somehow excitations around the thermal state. So we can perturb the system in a simple way and watch it decay. And this oscillates with particular complex frequencies, and these frequencies are kind of a signature of the black hole. So you can call this the black hole seismology. So you shake it a little bit and you see how it shakes. And in analogy with, let's say, helioseismology, which is the same thing for the sun, for example. Now, there are some general features of these quasi-normal modes that are fixed by the similarities we're talking about. First is that the lowest frequencies are of order the temperature. So it's basically the only scale that we have. And these lowest frequencies have both a real and imaginary part. Also, there are relatively few modes with these frequencies. So we in particular, we don't have n-square modes, which have an order 1 of modes. So this shows that when you shake the system, the long-lived excitations are very collective excitations of all the degrees of freedom that we have. So we have a large number of degrees of freedom, but a small number of oscillation frequencies. And this is not quite what we find for the ordinary systems. For example, if you have a bell or a sun, the frequencies are much lower than the temperature, right? So in both the bell and the sun, there are some very collective excitations, more like hydrodynamic excitations. And they have a much lower frequency because in both the bell or the sun, the interactions between the different degrees of freedom are very localized. You don't have sort of all-to-all interactions that couple the various degrees of freedom as we have in this matrix model. So in particular, there are no light hydrodynamic modes with frequencies much lower than the temperature. Now, calculating these quasi-normal modes is a well-developed subject. Now, these remarks are true for any black hole, even for Schwarzschild black holes in nature. These remarks are also true. Now, here I said temperature, but the temperature for a Schwarzschild black hole is 1 over the size of the black hole. Well, now calculating these quasi-normal modes is a very well-developed subject, and we are supposed to expand all fields around the black hole solution and get some wave equation. So this is in principle conceptually straightforward. Mathematically, it's a little complicated because of all the indices that the metric has and so on. And in this particular example, there is a nice mathematical trick that involves the scaling symmetry that gets us the wave equation. So I perhaps will explain that trick later, but we can find, for example, all these quasi-normal modes. And so they are in units of the temperature. They are some numbers, okay? They have both a real and imaginary part. They are almost, they are the same order of magnitude. And you can find them. So you can find them. And I mean, here, we find them to very high numerical precision, just to show that it's a well-defined number that one can compute. Of course, if you are interested in these numbers to compare with the output of some numerical simulation and so on, you would only be interested in the first few digits. Now, this is a prediction. You can view this as a prediction for the quantum system, and it depends. The prediction depends on detailed information about the geometry of the black hole, on this particular black hole solution, and so and depends on solving Einstein's equations and so on. And so if you had a quantum simulator and you computed these frequencies, the evidence that we have some black hole would be comparable to somehow the evidence we have for astrophysical black holes, in the sense that, for example, from gravity wave signals, we see that there are two objects that are colliding with each other, and then the particular form in which the waveform decays after the collision depends precisely on these quasi-normal modes, and matching these quasi-normal modes to the prediction from Einstein theory is some evidence that the final object that you make is actually a black hole. Okay. Now you might say, well, this black hole you make in the quantum simulator is not really a four-dimensional. It's not a real four-dimensional black hole, and this would be absolutely correct. It's definitely not a real four-dimensional black hole, but it would be a real 10-dimensional black hole. Would match the predictions for 10-dimensional Einstein theory. So one can view it as not necessarily a test of quantum gravity in our own world, but some interesting phase of matter. So you can make a syntactic phase of matter that is described by Einstein's equation. It's kind of, it could be like a very sophisticated version of a Bose-Einstein condensate. Bose-Einstein condensate is also an interesting phase of matter, but of course it's simpler because it doesn't rely on any interactions. But this is a more interesting phase of matter that relies on interactions between the different qubits. So let me have some conclusions so far. So we discussed that there is a quantum mechanical system that has a 10-dimensional gravity dual. At finite temperatures is related to black holes, and gravity predicts various thermodynamic properties, the energy, the temperature, the entropy, etc. And gravity also predicts the quasi-normal mode frequencies. And it's an interesting synthetic phase of matter. Now, there is a theoretical challenge, which is to understand how space-time and the Einstein gravity action arise from the quantum system. So that's something we currently do not understand. So this is, well, a problem in ADS-CFT always, how to understand in a very direct way how this happens. And maybe having those quantum simulations might help us understand this. Or perhaps with theoretical methods, we can understand it before they actually do the quantum simulation. Are there any questions? Okay, so now I will explain a little bit more in detail the trick that was used to solving this quasi-normal mode computation. So the idea is that so when you write the action in this way, where the scalar field appears multiplying the overall action, this looks similar to what you would get if you had a theory in higher number of dimensions, and this factor here was the volume of the extra dimensions. Okay. So when you do that, then the factor you get in front of this term will depend on the actual number of extra dimensions you have, and you can adjust the number of extra dimensions so as to get the factor that you have here. And when you do that, then you get some kind of fractional number of extra dimensions. And so you can formally think of the solution as as an ADS2 plus delta times SH. So it turns out that the number of extra dimensions is delta, the same delta factor of, but this should be 9/5, not 5/9. So the same exponent that we had before. So that's this. So the zero temperature solution then is some ADS space. And then the non-zero temperature solution is just the usual ADS black brane, where you have some function f, which involves the coordinate c to some power that involves the number of dimensions. Now, everything that we'll do it will be independent of this coordinate. So the fact that there is only a fractional number of coordinates doesn't really matter too much. It doesn't matter at all. But then we'll get that the entropy is proportional to t to the d-1, as we always have in ADS-D. And that's also the factor of, this is also what we had before for the logarithm of the free energy. Okay, so we can find the spectrum of excitations of the theory at t equal to 0. So this was done a long time ago. You also, in the latest paper, we simplified this derivation by thinking about an 11-dimensional point of view and plane waves and so on. And that gives the masses of the fields, or the scaling dimensions that we have in this ADS picture. And then it's a simple matter to write the wave equation at finite temperature, just that's the equation of a massive scalar field in that number of dimensions. And we also check that this gives the right answer for some mode, for one particular mode, by the direct expansion of the 10-dimensional equations. So this is here we end the discussion of the wave equation. Now I'm going to, well, is there any question? now we'll discuss another issue, which is the question of whether we can calculate this scaling violation exponent from the matrix model. Okay, I said this was a non-trivial property of the matrix model, so one would like to understand how it can be computed. So, I'll discuss an argument which assumes that there is a symmetry at strong coupling, that there is a scaling symmetry of this type, a scaling similarity. And then once you make this assumption, we'll calculate the exponent, okay? So ideally, in an ideal world, we would also like to explain why we have the symmetry at strong coupling. So we're not going to explain why we have the symmetry, we're only going to assume we have the symmetry and then derive what the exponent is. And the idea will be to look at a specific observable and use supersymmetry to relate it to a weak coupling computation. So in fact, the observable we are going to discuss is basically probe branes moving in this geometry. And or you could view this as multi-center solutions of the, well, or more precisely in the matrix model, we could think that we are giving an expectation value to the scalar fields, and we are looking at the Lagrange reaction of those objects. So if we look at this, then we'll find, and so in ideas in some number of dimensions, we'll find that this is the action, and we can redefine this. So in general, if set, we can define the web in such a way that it scales under the similarity in the same way that the time scales. And with that language, the expansion will have this form just by scaling. And then we can redefine this variable C so that the kinetic term is simple. So C will be related to some variable I will call R in this way. Now, if we, on the other hand, consider the problem at weak coupling, we can expand around sort of slowly moving configuration. And then we have a term that looks like R dot squared, and then there is a one loop correction that generates an R to the fourth correction. Now, it turns out that supersymmetry implies that there are no further corrections to the V squared term, that is to this term, or to this V to the fourth term. So, so this is valid even when we go to stronger coupling and we have this slow motion. And so that means that these two actions should actually agree with each other. And for them to agree, then it means that this D, which was the fractional number of dimensions, should obey this equation. And this implies that D should be equal to this, which implies that this delta should be 9/5. Okay. Now, a calculation which was in this neighborhood was done by Smilga, and then also in this other paper for other DP branes. And so this is, I think this is a slightly more clear version of some ideas that were in those papers. So in conclusion, the idea is that if we assume that there is a gravity solution with a scaling violation exponent delta, then we computed this exponent delta from the matrix model. And yeah, so after we wrote our paper, we were contacted by some Nikolai Bove and some other authors who have done a different computation, which was the computation of a sphere partition function for DP branes. And one could also use their computation to fix this exponent. And we'll include that in the revised version. Okay. So as I mentioned, this story about the scaling symmetry and the higher dimensional ideas works for all DP branes. Now I'm going to comment about well, the spectrum of dimensions. I mentioned that it was computed in this paper. The dimensions have a very simple expression, so similar to what you get for ADS 5 times S5 or the simple ADS examples. So there is, as you increase the angular momentum, the dimensions go like some factor, this factor 2/5. And that this factor is just the square root of the factor that Jeff was asking me before that was incorrect, that should have been 25/4. So that's the same factor. And then there is some other factor that, well, depends on the type of field that you have. So when you, anyway, and you can get this very simply from from an 11-dimensional point of view. Won't discuss it. Now we can use these dimensions to ask the question of how much you need to fine-tune this Lagrangian in order to get this theory. Because if you imagine trying to simulate this Lagrangian or even doing numerical simulations, you might worry that well, the question is whether this model is very fine-tuned or not. So how many relevant deformations are there? So if you make small mistakes, how significant are they? So that's the question of how many relevant deformations there are. And the good news is that there are only a relatively small number of relevant deformations at strong coupling. If we were at weak coupling, then any power of the field would be relevant. But when we are at strong coupling, because the dimensions are of this form, we only care about the ones who have dimensions delta less than d, so delta less than 14/5. And so this is an argument based on the similarities. And if we demand SO9 invariance, then there is no single trace operator. So that's kind of good news. There are a few double trace operators. So if you just only impose SO9 invariance, and of course, if you don't have SO9 invariance, then you have a few more operators. And this would need to be fine-tuned. Now, I mentioned that the original conjecture about the relation to gravity was for the SUN singlet sector that was related to gauging the SUN. But if you wanted to make this in some simulator, the SUN symmetry will not be perfect. And we think that if you make perturbations, well, first of all, there is some evidence that the SUN non-invariant states would have high energy, so we don't need to impose a singlet constraint. But even if you wanted to impose a singlet constraint, you could add also terms to the Lagrangian, which are proportional to the Casimir of SUN to raise the energy of the non-singlets. So that's really not a problem. So you can treat it essentially as a global symmetry. Now, the problem might be that you have some terms in the Lagrangian that might break the SUN symmetry. And you could ask what's the effect of those terms. And we really don't know, but we suspect that they are probably relevant when we go to strong coupling. Okay, so we've discussed how to use the symmetries to classify the operators, and we can separate them to relevant, marginal, and irrelevant as in conformal cases. So this is something that uses the scaling similarity, and we can use their dimensions to understand how much we need to fine-tune their problem. And one good news is that there are less relevant operators at strong coupling than at weak coupling. This is something that was noted already about n equal to 4 super-Young males by Mats Strassler. That's also true in that example. Okay, so the final conclusion is that this is an interesting quantum mechanical theory that can be used to understand the emergence of a space-time governed by Einstein equations. Okay, thank you.
Thank you very much. Any questions?
Yes. Hi.
Hey.
So you made a comment earlier, on in the talk about the estimate of the number of qubits you'd need to simulate a quantum to simulate a quantum system like this. I mean, the question is essentially how far could you get by trying to coarse grain this kind of model, somehow throw away some detail and use and do with a smaller number of qubits, and if there's a way to take a matrix model like this and get a feel for just how much how many less you could I suppose the question is like how much coarse grading of this kind of model would be too much.
So the short answer is I don't know. I mean, of course, it's an interesting question, and if you really wanted to simulate this, you would need to start exploring that question. So some of the same authors that did the numerical calculation have started thinking about quantum computations, and like the state of the art is trying to get a model that has, let's say, two matrices, two bosonic matrices. So that gives you an idea of what people are trying to do now. But yeah, it would be interesting to know how you can simplify. That there is some other aspect that I didn't discuss, which is how easy or difficult it is to implement this Hamiltonian. So Hamiltonian has many terms. So it has millions of terms. And so that might be another problem for realistic simulating. I mean, it might be that instead of a general purpose quantum computer, you might have a simulator similar to these quantum simulators people are constructing for the Hubbard model, for example. Maybe there is one that you could construct for this model. And this might be a more, perhaps another interesting way to analyze this problem. But yeah, you would need some tricks to, you know, to put these interactions that are basically like the matrices, which involve all the qubits with all the qubits, and so that's a little difficult.
Oh, okay, thank you.
Yeah, sure.
How does this picture gel with for example the simulations that Jafaris et al. have done with the SYK?
Right. So those are simulations of theories whose gravity interpretation is not clear. So, well, where the gravity, so they are related somehow to, in principle, they are related to JT gravity with some matter content, which is doesn't obviously have a local action in the bulk. But yeah, so SYK is a simpler model to simulate, and has gravity, and the gravity in those cases, it's simple, it's not dynamical, there is no bulk graviton mode. There is, and it's basically a boundary mode, this Schwarzian action. And yeah, so that's a simpler model to simulate. So I mention in this model because I think this is the simplest that has sort of an Einstein gravity, you know, a space-time that is more conventional.
Yeah.
So that there might be other, I mean, there might be other models that are that involve extremal black holes and maybe with some internal dimensions or even without, but that have a local action in the bulk. There might be models like that. I mean, in principle,
that are easier to simulate, or?
Well, I mean, whether you could simulate them, or it depends on what you want to learn from the simulation. So,
right.
In their case, they wanted to have this teleportation by size. Let's say some particular type of sort of chaos-driven teleportation. And then they had something of this. Well, it's not clear they even obtained that because the model they had was integrable. So the Hamiltonian they simulated was an integrable Hamiltonian.
This was SYK2.
Yeah, it was SYK4, but they truncated they set to zero many of the couplings, and after they set to zero many of the couplings, the resulting Hamiltonian was the sum of many commuting terms, because it was many commuting terms. It was an integrable Hamiltonian. So, well, there is a bit of a debate on whether, yeah, it is or it is not this teleportation by size. But...
Right. There seems to be internal to Harvard debate.
Well, I think it would be more clear if the Hamiltonian you are simulating is chaotic. And but well, this is what they can do now. I think this is a kind of a first step, maybe adding a few, but once they have a slightly bigger machine and so on, they will be able to do it, I suppose.
So what about something, I guess, I don't know whether this is simple or not, but Ising model with transverse and longitudinal excitations is chaotic, right? Like Schenker and Stanford, and
Right.
would that be
Well, I think people
Yeah, to
simulate all
simulate,
kinds
or-
of spin chains with various Hamiltonians, and not in the quantum computer, but with quantum simulators. So, for example, I know in particular the Lukin group at Harvard. They simulate this type of spin chains, and they even found new phenomena like the so-called quantum scars and so on. Yeah, they do that. So here, this Jafferis et al. Group, they wanted to do teleportation, so teleportation between two quantum systems, which is interesting. I mean, this goes even beyond black holes. It's more sophisticated. So the questions I was discussing here, quasi-normal modes and so on, are very simple compared to teleportation. Is a more interesting sort of quantum phenomenon that has to do with wormholes and traversable wormholes. So in a certain sense, their setup is exploring more interesting quantum system, more interesting, quantum behavior and connection with wormholes and so on. Here,
So is the idea that in a fully simulated fully simulated quantum model from the matrix model, you'd be able to reproduce, for example, the quasi-normal mode spectrum, or
yeah, that's the idea. Yeah.
I see.
And those are some real-time things that are maybe harder to do with ordinary numerics.
Right.
But it might be that they can also be done using ordinary numerics by some interesting trick. So.
All right. Sorry, let me just check if anybody else has any questions. Anyone else questions?
Yeah, sorry, if I could
Sure,
ask
go ahead.
one small question is that as you were giving the talk, you had this this picture of the 9+1 space-time with this
Yes.
with this black hole and the thing that grows, and then as you lower the temperature, this neck closes.
Yes.
Is there a comment that can be made about how, as you lower this temperature, somehow how quickly that neck
Yes. All of that can be seen completely explicitly. We have the precise solutions, and one can answer all these questions. The solutions were originally found by Horowitz and Strominger many years ago, so you can answer these questions.
Okay, thanks.
So, Mark Hanno gave a talk here a little while ago about his work on chaos and chaotic solutions and stuff, where they're really talking about chaos, I guess, in the vicinity of a singularity.
Yes.
And so it's a little bit interesting.
That's different than the chaos I mentioned.
Right. So I'm not sure how to think about this story. Right. I mean, the chaos that you're talking about and the chaos that we kind of appreciate with JT and stuff. This is stuff that's taking place at the horizon.
Yeah, exactly. Yeah. That's what.
And it's quantum.
Yes.
Right.
So, I mean, it's also in some sense classical. So in the dual theory, some kind of quantum chaos.
Yeah.
But from the point of view of classical physics, from the point of view of this near horizon geometry, it's really tree-level classical scattering between particles. classical gravitational scattering.
Okay. Okay.
The
Well, that
scattering,
makes more
the
sense.
scattering via shock waves and so on.
Right.
Yeah.
I mean, it
So
still strikes me as a little bit strange that when you get close to the singularity, that classicality persists.
yeah, it might be that the chaos that Heno and company are talking about is related to some chaos in the quantum theory, but that's something we haven't understood how
Yeah.
it's related.
Right. And just as an aside question, since I have you in the room, how does all of this fit in, if it does at all, with the magnetically charged black holes that you were working on some time ago? Was that just a side interest project?
No, well, it doesn't. It doesn't in any obvious way. So the magnetically charged black holes are interesting black holes we have in the standard model, and they can be used to make wormholes and all kinds of fun things. But well, we don't know exactly what their quantum mechanical duals are. So they are not. I mean, they're interesting configurations, but the type of question I was asking while during this talk are different than the type of questions one would ask about those magnetically charged black holes. I think those are like interesting fun configurations that you can have in the standard model. Now they are hard to produce, so I'm not claiming that we probably are likely to see them. Probably we're not likely to see them.
Right.
And you can wonder whether so one interesting feature of those magnetically charged configurations is that the matter of the standard model leads to, when the charge is large, leads to lots of two-dimensional massless fields, effectively massless fields. And that's something I don't know. I don't think it happens in any example I know with supersymmetry. So because with supersymmetry you also have scalars, and maybe it does happen. At least thought a bit about it,
But these are not modular or anything, are they? With flat directions. I mean, these massive scalars.
Well, this yeah. Well, typically you don't have massless particles that are charged under the gauge field.
Right.
Maybe if you go to special point in moduli space, you can actually find them. I haven't tried too hard, so maybe they have some interesting effects, and I might try to see whether there is a supersymmetric version of this that might be
right.
But in the typical, I don't know, type 2 supergravity theories, then you don't have massless charged particles at the generic points in the moduli space. Either bosons or fermions. And in some of the simplest points in moduli space, you also have charge vector fields, and that would be a problem. So you would need to have just charged matter, which does not include the vector multiplets.
Right.
Yeah, maybe it is. Maybe there is some way to do something interesting with supersymmetry. Something where you have this phenomenon, and in addition, it's computable in some interesting way. Might know. Yeah.
Well, thank you. If there aren't any more talks, if there aren't any more questions, let's thank Juan again for a really good talk. Thank you very much. I just to continue our conversation before the talk started. I see that let me see, it was here just now in section 3 of our paper, I think.
Right.
We work out the correlators for the supersymmetric theory in 0+1 dimensions.
Okay. Yeah. I'll
but I think that I'm not sure how many supercharges were present.
Well, first I have to see whether it's the same model that we are looking at. But
right. yeah, it was section 3 that we'd computed that.
Right. Yeah. Okay. Yeah. That's
Right. Well, thanks
well,
so much for the talk. It was really interesting.
sure. Yeah. Enjoyed it, and best wishes to all of you. Bye-bye.
Okay. Thanks, everybody.
Thanks. Bye.